Artificial intelligence is an arena that is rediscovering our future in technology. In our previous video, we gave an in-depth explanation as to how realistic environment modeling takes place within our simulator. Our focus today will be to introduce the process behind replicating realistic human behavior and movement patterns. From stacked histograms that reveal the numbers of occupancy at different locations and transportation methods used throughout the day at specific time periods, to personal mobility data analysis that showcase mobility patterns of individual agents based on their occupation, our simulator engine, PD-Sim, will be able to unravel the secrets to modeling real-life human routine behaviors with the use of data that we collected from various demographics including GPS trajectories. Watch to find out how the mechanism behind this AI-powered process unwinds.
We model these people into two categories. The first category is the transporters and the other category is the travelers. So basically the transporters are like bus drivers, taxi drivers and office bus drivers. They tend to move around the environment, and they travel the other travelers with them. So for example, the bus driver can travel like a different set of people with him. So this is very useful when we are modeling the mobility in the simulator, because there are a lot of interactions that are happening inside a bus, like a public transport, because of the social distancing and using masks. Those kind of factors come into place when the people are traveling using public transport. Therefore, we need to consider these kind of transport related factors when we are building the simulator. Therefore, we have these kind of two main categories when we are modeling the people. And of course, all these people have like a gender, age, and a different route that they are taking, and everyone has a home and a working place. Also, they have like the COVID-related stuff, like the immunity, whether they are asymptomatic, their disease state, their disease severity, the infected time. So all these kind of information are stored in the simulator for each person. So when we are building this simulator, we need to make sure that the people move in a more realistic way. Therefore, for example, if we take a different type of person, like a commercial worker, we need to make sure that their daily routine is more similar to actual commercial worker. Like they need to go to the working place in the morning, and they need to come back in the evening, and they need to have a different kind of routine inside the working area, like that. So what we did was, we need to at the beginning of the day, for every person will get a different daily routine, and they will go to each of these locations, and they will stay for the given period of time, and they will leave to the next location of the routine, and like that they will complete this daily routine, and we will see whether this their motion reflects a realistic person's daily routine. So how we are going to build this daily routine is that we have like two matrices to build this daily routine. For example, let's take a commercial worker. He has here, if we take a commercial worker, he has the probability of staying at home at the beginning of the day, and this is the end of the day. And in here we have the time in minutes. So at the beginning of the day, like 12 a.m., he's more likely to stay at the home, and at noon he will go to the working place, and at the evening he will come back to the home. So this is what is given. This is also the same graph given as a line curve. So in the morning he's more likely to stay at home, and in the daytime he will go to the working place and come back home at the evening. So if we consider a time t, there are two probabilities: a probability of staying at the working place and the probability of staying at the home. So what we are going to do is we are going to take these two probabilities, and we are going to sort it in the descending order, and we're going to put it in the x-axis of a Poisson distribution, and we are going to select a random number. So after that, we can identify if that falls under 0 and x. That means that he's more likely to go to the working place. So like that, we are going to select a location based on these two matrices. So we can like add different kind of places like a park, a medical zone, or a hospital. Like that, we can add different kind of places to this matrix, and we can identify where they are going at a particular time of the day. So after selecting a particular location, so let's think that we have selected the working place, and at time t he will go to the working place, and we need to figure out how long he is going to stay there. For that, we are using another matrix which is called the occupancy matrix. So that shows if you're going to the working place, we extract that out, it will look like this. So what it says is, if he is going to a working place, he is more likely to stay for around 40 minutes or around 80 minutes, or somewhere around 0 to 30 minutes. So it will select a random number based on this probability density, and we will add that to the daily routine. So if he's going to the working place, he will stay around there. Let's take 40 minutes, and after 40 minutes we are going to the t plus 40 minutes and see where he will go next. Like that, we are going to build the whole daily routine for each person, and then we are going to simulate it afterwards. So this is an example of the visit probability matrix in the simulator. So this is for a student class. So he will go. So for example, this small dip in the middle is the interval or the break that they have at 10:30 to 11, as you can see here. So like this, we can like give this input very intuitively using a user interface, and we can draw these curves, and we can see that whether the simulator mimics this kind of movement in the simulator, and I will show that the results of our simulator in the upcoming slides. So let's think that for a given person, the daily routine is first going to this house 1, and the second thing is going to this park, and the last thing is going to this shop, and then after that he will come back to house 1. So the house 1 is given here, and the park is given here, and the shop 1 is given here in purple color. So what he's going to do is he's going to go from this house 1 to the park to the shop 1 and come back to the house 1. So what happens here is there's a specific route that he can take in the location tree structure, and what he's going to do is he's from the house 1 he's going to the parent of that tree node, which is the houses section. So after that he will go to the park, and he will go to the residential zone, and he will go to the commercial zone, and he will go to the shop one, and he will come back to house. So this is the basic route that they're going to take if we give different destinations in the simulated environment. So of course he's going to move like these random movements when they are at the park, and he will go to these destinations when they're going from place A to place B. Yeah, so these are the two kind of movement patterns in the simulator. So if they are staying at a given location, we can define different kind of motions, like a random motion or something like that, and they will use different kind of movement methods, like for example, if they are in a park, they are more likely to walk, and if they are moving from a park to a commercial zones, they will more likely to use a car or a bus. So the two types of movement methods are like movement inside a location and movement within locations. Therefore, we need to categorize these movement methods into two different classes, which are called dependent transport systems and independent transport systems. So one person in an independent transport system, for example, if he's using a car, he can go around to different places without help of anyone else. But if someone is using a transport system like a bus, he need to wait until a bus driver comes, and that bus driver should take that person to the destination place that he wants to go. So these dependent transport systems, they have drivers. They're like what we call the transporters, and those transporters are responsible for moving the travelers within the environment. Therefore, this creates kind of two different areas or surroundings when the agents are moving in the location structure. So if someone is using a dependent transport system like a public bus, there are different kind of interactions between them, and that is reflected in these kind of transport systems. Therefore, we can add different kind of parameters that rely on the disease spread, like infectiousness, the social distancing inside the bus, the hygiene of people inside these transport systems like that, and different capacities in the transport systems. So we can vary these parameters and see how the disease spreads when we run the simulation. Also, I need to note that these different kind of transport systems are independent of each other. So, for example, if someone is using a car, that car cannot infect or like come into contact with someone who is using a bus, because they are in two different vehicles. So when they are moving around, so they are more or less isolated from each other. Okay, so there are like different levels to these movement methods. So for example, if something is if that movement pattern is private or it's more towards independent movement, it has a very low value. We have assigned these values, and a larger value if this is more towards a public or dependent movement. So we have assigned these kind of values to these movement methods because, for example, if someone is going by bus, and if a bus doesn't comes for like, let's say for 2 hours, he's not going to wait until forever until a bus comes, right? He's going to either go to a train or a taxi, and like that he's going to come to a more lower level of an independent movement, and he is going to take some kind of other movement methods to go to their destination. So therefore we have assigned these kind of values to these movement methods. So therefore, these dependent movement travelers can travel using other transport methods as well. This way, we don't end up with people who are stuck at different locations, because that doesn't happen very oftenly in real world. So we have implemented this kind of override levels to these movement methods.
Do leave a thumbs up and subscribe to our channel if you liked the video. And don't forget to stay tuned with our playlist if you're interested in finding out more about the simulation engine at PDSim AI for COVID.